Welcome to the ME503 module on mechanical governors. Let's start with a practical engineering problem. When an industrial engine, like the ones powering massive electrical stations, experiences a sudden increase in external load, its rotational speed drops. To solve this, we use a mechanism that automatically controls the supply of working fluid. By physically adjusting the fuel intake, the governor keeps the mean engine speed within strict, safe operating limits as that external load varies. Let's trace the mechanical anatomy. The kinetic chain moves from the spindle to the flyballs, sleeve, bell crank lever, and throttle valve. As engine speed increases, faster spinning forces the flyballs outward, lifting the sleeve and closing the throttle valve to reduce fuel. The entire mechanism acts as a purely mechanical feedback loop. The engine's physical rotational speed directly dictates the valve adjustment, forcing the system back into equilibrium without requiring any digital sensors. Before we go further, we need to address a frequent point of confusion. Both flywheels and governors regulate engine speed, but they operate on completely different physics and timescales. A heavy industrial flywheel relies on its massive weight and rotational geometry to operate within a single cycle. A flywheel strictly controls the rapid intra-cycle fluctuations caused by the engine's internal turning moment. A governor handles the speed variations caused by external load changes over many cycles. This chart classifies mechanical governors into centrifugal and inertia branches. We are focusing on centrifugal. Industry moved past simple pendulum watt governors for more control, leading to loaded types, specifically deadweight Porter and Pro-L models, and spring-controlled variants. So, while the flywheel smooths out the engine's internal energetic pulse, the loaded centrifugal governor acts as the engine's long-term external throttle manager. Let's map the geometry of this system. The height of a governor, denoted by H, is strictly the vertical distance from the center of the flyball to the exact point where the arm axes intersect the spindle. When the governor runs at an equilibrium speed, the outward centrifugal reaction is perfectly balanced by an inward radial force. We call this the controlling force, or FC. In loaded models, this inward force is provided by the downward weight of the sleeve. Let's test this concept. Pause the video for a moment and think through this chain reaction. If an external machine suddenly stops drawing power from our engine, what exactly happens to the centrifugal force and the sleeve? Because the load dropped, the engine speed jumps. That increases the centrifugal force, pushing the flyballs outward, which forces the sleeve up to choke the fuel supply. This brings us to a theoretical limit called isochronism. An isochronous governor possesses infinite sensitivity, meaning its range of speed is exactly zero. N2 equals N1, which mathematically demands that the height at position 1 exactly equals the height at position 2. But watch the physical geometry of a Porter governor in motion. As the balls move horizontally outward to a wider radius, the rigid linkage forces the geometric height h to decrease. You cannot push the balls outward while maintaining the exact same vertical height. Because of this mechanical reality, a gravity-loaded Porter governor cannot achieve isochronism. And practically speaking, even if it could, that infinite sensitivity would be disastrous. The slightest speed deviation would slam the sleeve from one extreme to the other, causing the engine to violently hunt between maximum and minimum fuel states. At steady speed, zero net force acts on the sleeve. Force appears when speed changes. This effort is the mean force exerted encountering resistance while sliding. Moving the sleeve performs work, called power, calculated by multiplying mean effort by vertical distance traveled. This summary grid lays out today's 4 pillars. Quadrant 1 covers the kinetic feedback chain. Quadrant 2 marks the strict boundary between internal flywheel control and external governor control. Quadrant 3 maps the centrifugal classification tree, and Quadrant 4 contains our dynamic operating constraints. Mastering these specific mechanical linkages and dynamic definitions gives you the precise foundation required to analyze complex controlling force diagrams in your upcoming engineering lectures.